Is it audible?
Yep.
Oh, okay. So good day, everyone. There was a lot of interesting discussions this morning, and this presentation actually dovetails nicely with the earlier one by Raghu, as well as the one prior to that, in terms of some of the challenges that need to be addressed in terms of moving away from traditional networking model and then trying to put more computation on the network. So this is, the work that we are going to be currently presenting is more along the lines of infrastructure support. What are the things that need to go in the software API? So as part of that, we will be describing certain changes that we think make sense for the OpenFabric interface and how it is applicable to the next generation of Smart NICs. So we're going to divvy this presentation into two parts. I'll cover some of the terminology and the hardware portion to the extent of how much I can squeeze in 10-15 minutes, and then Sean will be taking over in terms of the real work, in terms of what needs to go into the OFI API to support this model. So let's start off with some terminology. I know this is somewhat vague. When you ask people what a Smart NIC is, it depends on who you talk to. In fact, even within Intel, depending on the division that you talk to, they have their own vision of what a Smart NIC is. So maybe some of you might not agree with this definition, but it's open to feedback in terms of how you think whether this makes sense. So before we discuss what a Smart NIC physically needs to look like, let's start off with what are the requirements for a Smart NIC, and sort of we put together some of the requirements for a Smart NIC. Needless to say, a Smart NIC has to support traditional networking. So that's the baseline. Without that, it doesn't qualify to be a NIC. And then the smartness comes in play when you're actually combining the computation and the networking together as a single entity. So that's the second requirement. The third thing is it has to be smart in a way that it should be adaptable. It cannot be a complete something baked in silicon and one-stop shop. For instance, we had the Amazon presentation on SRD, for instance. Tomorrow they might decide to change the protocol, to change some bit somewhere. So you need to have that capability at the adapter level to make sure that it actually goes along with all the new developments that we are looking at in terms of not just networking protocols, but also from an application standpoint, what you might want to offload onto the network itself. So that's the other thing. But the most, I wouldn't call, I don't want to sort of rank all this. Because it's an OFI-based presentation, that's the part which we are going to focus on, where we need to standardize the software API. Each company cannot come up with their own proprietary way of going about programming Smart NICs. And the way that we are looking at Smart NICs deployment, it's just not going to be simply at the processor, a Smart NIC attached to a processor. There are going to be different deployment models for that. So we need to make sure that everybody talks the same language. So in other words, there's going to be compatibility between different vendors. So that's one of the things that we're going to be focusing more in this presentation. So why do we need a Smart NIC? Of course, I'm probably preaching to the choir here, but it's sort of obvious reasons. If you look at the cloud providers, they want to get the maximum bang for the buck in terms of if they buy Xeons, they want to make sure that the customers get 100% of the Xeons. So they want to offload some of the grunt work in terms of the infrastructure, what we call as infrastructure work, to a secondary device. That's where Smart NIC helps. If you're doing a lot of communication and you want to do certain computation as part of this communication, why use the Xeon cores? Just let's do it at the NIC itself. So that's one reason. The second thing is, of course, it's just not communication alone. There are certain aspects of the computation itself that can be offloaded onto the NIC. So which means that, of course, you need to think in terms of how to redefine the algorithm and change the application. But here is an opportunity where you can offload it onto the network itself. So there was a presentation yesterday on doing computer network. So this qualifies as part of that. And then the agility that I already touched upon in terms of you want to be very flexible. Most of the folks know how hard it is to come up with a new silicon. It takes years. And once you do it, you got to make sure that it has a certain lifetime. But the new generation of algorithms, new generation of applications that are evolving, they change so rapidly that putting it in silicon is not a good idea. So we need the configurability and the agility. So that's where the third requirement comes from. So then, now that I've described why we need a smart NIC, this is the most challenging slide of the lot. I mean, again, you might decide to disagree. I mean, I don't know if folks have heard of the story, Blind Man and an Elephant. Any of you heard of it? It's an Indian story. No? Okay, there are two reasons I want to tell that. One is because it's probably close to lunchtime, so maybe just to get your attention. And the second thing is smart NIC somewhat falls in that category. Of course, I mean, unlike the story, I mean, you can Google it later. Unlike the story where all the blind men think of the elephant in their own way, here I think everybody is correct. I mean, depending on who you talk to, that's the term for smart NIC. So what we decided to do is collect all these definitions and sort of, create a taxonomy of what a smart NIC looks like. So depending on where you're coming from, perhaps you're building a SoC-based smart NIC, which is an ASIC, which has some programmable core sitting in it. So maybe that could be a smart NIC. Alternatively, you could have an FPGA SoC. I mean, whether it's Intel Altera division or whether it's the Xilinx division, you could have a FPGA with again embedded cores in it, and then it provides a direct network interface. So that's one part of the smart NIC domain. The other, that's an SoC, which means that it's an autonomous. You don't really need a Xeon processor or a separate a processor. I mean, I keep saying Xeon. Of course, it could be an AMD processor too. So you know why I'm saying Xeon. So it could be a process. You don't need a separate processor for managing the smart NIC. So it's an autonomous node. So this actually has a very interesting usage model in the future. I'll give an example later on why this is very useful. And then there's a discrete option. I mean, all along we've been talking only about the discrete option where you get a smart NIC and you probably plug it into a PCIe card on the host system, and then you use it for whatever reasons, including offloading some of the compute onto the NIC, and then it connects to the network. So that's the discrete option, which again can come in three varieties. A standard ASIC, that could again be a elastic fabric adapter. I'm assuming it's an ASIC, I suppose. It's not an FPGA. I don't know. I didn't get it from the last presentation. So let's say it's an ASIC, but it's got some intelligence. It's got some cores, so you can probably go and muck around with it and change the protocol. That's one option. The second option is maybe an FPGA acting as an assist to a traditional NIC interface. I mean, a lot of you must have heard of this Microsoft's Catapult project, where an FPGA is sitting next to a traditional NIC, and the FPGA provides some of the acceleration capabilities. At the same time, it measures nicely with the NIC itself. So that's one option. And of course, the third option is the FPGA itself acts like a NIC. So I mean, I don't know if you're following some of the FPGA technologies. It's becoming very aggressive. And I mean, I think the term FPGA is actually not correct, not clear anymore, because a lot of the hardened blocks that folks are putting on the FPGA makes it more like a hybrid ASIC. So part of the FPGA has got hardened blocks for providing network interface. It's got hardened blocks for some of the protocol infrastructure. It's got hardened floating point blocks, DSP blocks, you name it. I mean, you look at the static extent FPGA, for instance, you could see that a bunch of the silicon is devoted for hard IP blocks. Of course, it still has to qualify as an FPGA, which means that you got to be able to program it and you got to be able to configure it. So FPGAs are also going to be an interesting option to act as if they could be a discrete NIC in itself. And the advantage here is that it provides even more flexibility than what a traditional silicon could provide. So I just want to get a check here. I mean, did I hopefully cover everything, or is there something which is missed here in terms of what a smart NIC needs to look like? Of course, it's a broad umbrella here. If you guys have any input on it, maybe you can go and fix the slide and say, oh, we are missing that, and we can put it out here. Any thoughts? Okay, so looks like this covers all sorts of smart NIC capabilities. So having said that, I mentioned earlier about this one particular usage model of an autonomous smart NIC. When I say autonomous, I mean there's no need for a processor to manage it. So this is one example autonomous smart NIC. So here is a standard FPGA SoC which has embedded cores in it. And as I mentioned earlier, a bunch of these blocks, PCIe or the link physical layer or the memory controller interface, the ones which are marked in, actually I didn't use a correct color here, but anyway, the ones which are marked at the boundary are all hard blocks in the FPGA. And then in addition, you got this soft fabric where we can go and configure things for doing acceleration. So you can have the traditional, I'm not using the term RDMA, I'm calling it RMA. It's still remote memory access because RDMA has got this verbs usage model. So just to make it clear that it is remote memory access, whether it's verbs or something else, it doesn't matter. So we can start putting these blocks on the FPGA, including the specific accelerator blocks that are needed for the application. So with this in place, now you have a standalone Smart NIC, which can now be deployed in certain areas where it's simply not feasible to put a Xeon and putting a FPGA for a lot of requirements like cost, power, space, packaging requirements. So here is one example where, if you have looked at some of the HPC applications like particle detection, you have like two atomic particles colliding, and there's a vast amount of data which is generated, and then you're looking for certain specific behavior of this, that based on the collision. The amount of data that is processed is so much that you got to do the processing then and there. So the filtering has to be done then and there. And again, it's basically an A to D conversion which is happening, and FPGAs have that capability. But it would be a shame to just use the FPGA for only doing the analog to digital conversion. You can actually do much more than that. And that's where the SoC comes in, which means that you can do all the processing at the front end itself, and then send only the relevant data back to the back end for further processing. So at the same time, you want to make sure that the software stack running on the Xeon and the software stack running on the FPGA SoC talk the same language. It has to be standardized, and that's where Sean will come in. Okay, so one more last slide before I hand the mic to Sean. So in terms of the accelerator usage models itself that he'll be covering, we have sort of bucketized it into 3 pieces. In fact, the third piece is somewhat similar to the first 2. The 2 types of acceleration that we're talking about is inline and lookaside. So the inline model is as you're sending the packets on the wire, or as you're receiving the packets from the wire, you can do certain operations then and there. So if you use traditional RDMA, again, we had this discussion on what are the new things that we can do to RDMA. So here is an opportunity where when you do an RDMA read, for instance, as part of the read operation, you don't need to bring the entire data. If all you're looking for is certain fields in the data, let's do the filtering right at the NIC itself, and then send only the filtered data back to the memory, which means it saves on a lot of overhead on the Xeon processor. It's a lot of internal on-time memory bandwidth that can be saved, as well as the memory bandwidth that can be saved. So that's one usage model where we can benefit from inline. There's something called lookaside, which says that, yeah, of course I want to do things at wire speed, but there are certain operations which have to be done in an asynchronous manner, right? Like compression, for instance. You offload it, the lookaside churns at its own pace, and once it's done, without bothering the compute node, it can directly inject the packet on the network. So that's the second model that we're talking about. So these are the 2 important acceleration functionalities that we foresee in terms of a future Smart NIC. But there is a third feature which I think is going to be become very interesting, which is actually triggering these inline and lookaside on a remote node without actually having somebody managing it. So you can think of a bunch of these Xeon nodes with a NIC connected to a network, and then you can hang these Smart NICs off this network, and then you can specify what type of operation that you need to do. So if you're building a large database, for instance, the database itself can be spread out across all these Smart NICs on the far end, and the Xeon node can just trigger a key value store lookup, for instance. You can just send a key, and then the Smart NICs on the far end can do the lookup. But interestingly, these Smart NICs can communicate with each other independently. There's no need for somebody to go and orchestrate, oh, you do this, you communicate with this, or anything of that sort. So the Xeon can just start the operation, and then the operation will start proceeding independently on the Smart NICs. And then once the operation is done, the results comes back. So that's going to be one more interesting usage model for this. So that's it from my end. So let me hand the mic to Sean, and he will now describe how exactly we can go about doing all this. Thank you.
All right. So this is going to look at, hopefully, just kind of build off that to give you a background of what we're trying to do. and our overall objective of working with the Smart NICs and FPGAs. So the objective that we have here with OFI and what we're trying to change with LibFabric is how do we expose this sort of infrastructure up to an application? And we'd like to ideally be in a common way. And just to be clear, that one of the things we're not looking at, right, this is not an attempt to define a way to program an FPGA. That's not what we're trying to do here. This is not a way to offload to GPU kernels, right? So we're not trying to be CUDA. This is stuff that we're trying to link these sort of accelerations with the network transfer itself. And this is really kind of this presentation is really in joint with a couple other presentations we're working on within the OpenFabrics working group, which is how do we deal with heterogeneous memory, and then also what we've just started looking at is how do we deal with the accelerations in the network itself, like in the switches, such as collective offloads. So those three pieces kind of all fit together, but this is looking at really how are we taking advantage at really the endpoint side. So kind of going back to that same picture, we kind of looked at was what are the applications trying to do? And again, here it's very hard to say what is the application trying to do, because a lot of times the applications won't tell you what they're trying to do. Right? They want to use an FPGA, they want to do something programmable, they won't give you details, and it's a very wide variety of functionality that you're trying to support. So from OFI's perspective, one of the things I looked at was what's an example that we have that I can concrete, and I came up atomics. So OFI has atomic operations, and I try to use that as kind of if I took atomics and made it abstract, what would it look like? So these are kind of the higher level requirements we're looking at in terms of what the applications and how we need to implement this. So obviously we need some way for applications to discover, do you have this capability? Is there an FPGA present? What's available that I can use versus maybe what's active? And those may be different, and we'll have to kind of deal with that in the API. So I may have to actually program the FPGA, load a library or do some firmware update, or maybe I need to set up some communication, something with the ARM cores on the NIC in order to try to have this functionality available. So obviously, for any of these operations, we need to be able to provide input and get the output. Again, this kind of ties back and kind of maybe the heterogeneous memory piece. Obviously, if the input's coming from the host, that can be fairly simple. The input may be coming from some other device. Maybe it's coming from a GPU. Maybe the input's actually stored on the NIC itself. We mentioned the lookaside accelerations. So there may be some long-running functions we want to invoke. And then we want to be able to have those long-running functions, the result of those functions available for a transfer. And the API needs to be able to kind of capture this as well. So for the transfers, we may have it that every send-receive we do, every packet that goes out is going to have this acceleration applied to it. Maybe it's a filter, maybe it's an encryption, decryption. It may be that we want to be able to invoke the acceleration on a per transfer basis. So not every transfer is going to need this, but certain transfers that we mark need to have the acceleration. And the API needs to be able to adjust for that. Obviously, the acceleration could be local or remote, and if it's remote, that means that we're dealing with some sort of protocol in the network having to carry this information. So this is kind of a group of requirements. I'm sure there's more requirements that are going to come out, but this is what we're starting with to try to define what these APIs are going to look like. So our proposed vision, and we have no patches for this. This is all under development, so we're still talking about this in the OFI-WIG. So this is at least based on some internal prototyping. So hardware-based prototyping we've looked at to see does this concept even work? Typically with OFI, we've really been looking at what is the application doing and trying to drive those APIs down. This is a case where it's not very clear what the applications are trying to do because it's so broad. So we're really looking at kind of a next step is, can we define a general framework to expose these features up to the applications that all NICs or FPGAs can support? The applications can write to these, and we're hoping that this develops into more common sets of APIs and wrappers that we can build around this. Try to go quickly. So general proposal, from OFI's terms, like obviously we need some way to expose capability. So in OFI, we just said, okay, let's just define a new capability. And in my case, I called it a network function. So from an applications viewpoint, you can query and say, do you have network function support? And that's, again, very generic. It may mean that I have an FPGA locally. It may mean that my NIC has the ability to do the protocol to talk to a peer that has that Smart NIC capability. Beyond that, we start to try and define a set of what network functions do you have. Again, we're just starting to try to define this as a framework. So you may have one I have defined as like a chain, right? A network function chain. So if I need to apply two functions in order, I need to do a filter followed by compression, right? So how do I set up multiple functions I need to invoke as part of a single transfer? So that's one of the things I would call a chain. And we would add to this enum, right? As we create more common functionalities or applications need certain functionalities that more than one application needs, right? If it's data compression, if it's CRC32 checks, if it's data reduction, right? We can put this into our enum values, and these become just standard network functions. Otherwise, there's vendor-specific functions that can be exposed. And then we have this very generic structure that talks about the information. And this would be returned as part of, from OFI's do to an FI get info call. So FI get info, you get back a list of information about what sort of endpoints are supported, what sort of communication is supported. You do message, tagged, RMA. Added to this would be this additional network function information. And then with our network function information, we'd have different capabilities, different mode bits. It looks very similar to the other FI info structures that are being returned. So how does an app use it? We would introduce a new API. This would be at the domain level, where the application would say, okay, I've queried, I've found out what network functions are available, I've extracted the ones that I want to use, and then it needs to open the network function. So it opens a network function, and this would define, this is the type of operations that I want to have applied to data transfers, either on sends, receives, RMA, operations, whatever it is. This is the network function I'm going to use. And then it associates that network function back with an endpoint. And the reason for this is this gives the provider, if the provider, based on the implementation, if they need time to do any sort of setup, this is where they have time to do the setup. So that they don't just get a send call, and the send call says, here's a network function to invoke. This actually tells the provider up front that this is a network function I want to be able to use. So the application can bind the network function to an endpoint. They can specify as part of this binding that this applies to every send receive. It applies to all RMA operations that I'm doing, or maybe you specify that this will be really an on-demand type of operation. So whenever I submit a request, I'll tell you if a network function needs to be applied. So how do we apply it on the data transfers? So in OFI terms, we have a data structure, like all of our data functions, or functions have a context field. And today, we have different ways for the application and providers to communicate through this context field. It's just a general void star field. So when the network function flag is set as part of a transfer, that context field would basically be this data structure. And this data structure would allow the application to specify input and output parameters. Right, so if there's additional, if you're doing accumulation of some sort, or a reduction, or a filter that's being applied, this would be a way for the application to provide those input parameters to that function. If I'm doing a filter, what am I filtering on? This gives you either the structure or the integer that you're looking for, the floating point numbers. What sort of processing do you need to happen as part of the transfer? And for anything that's long running, OFI has this concept of triggered operations that's been extended for an object called a deferred work queue. And we can submit work requests to this deferred work queue as well. And this would be those lookaside operations where you would submit a request to say, I want to do some work, do the data compression, do the long-running filtering command, and then save the results. And then a future request would reference that operation for the transfer. So we would make use of the deferred work queue in order to submit these lookaside operations as well. So next steps, obviously this is kind of looking at a very abstract middle layer. How do we get the applications to at least start using this? We need to work at a higher level, right? So we wanted to have this common framework, but as we identify what are the network functions that are being used, what's a better API for the application to use? And those higher level APIs can be defined in terms of basically like static inlines that would wrap around these lower level constructs. But those need to be identified. Obviously, we want to coordinate this sort of change with heterogeneous memory. So if I'm invoking an acceleration, but the acceleration actually goes to a GPU, and the results are stored on a GPU or an FPGA that's detached from the NIC. How do I get that input data back to the NIC? And again, that's a separate kind of proposal we're looking at that kind of ties in with this so that we can make sure that if we have the acceleration off of the NIC, that we can still access that data, or we can even have the results come in from the NIC and then be placed directly into a GPU or NVMe device directly. And the last thing I had was, if you've followed my presentations the last few years, there's somebody I have been ignoring giving a call out to. So I'm going to give a call out to Susan. So, but she won't see this. So are there any questions? Again, this is still very early in our discussion. We don't even have patches available for this yet that have been released, so that's still under development, and we still have time to make changes and adjustments. Go ahead.
Hi, thanks for the talk. Since you have like a verbs provider for libfabrics, are you planning to map those accelerations to the verbs API?
So any accelerations that come through verbs, we would map, whatever we do at libfabric would map down to the verbs API's calls. So if there's accelerations and verbs, yeah, we would have some sort of mapping between those two to exist.
So you're saying if a customer or a user would like to have a less abstract or more direct approach, it can be mapped to verbs, and those accelerators can be used also on top of verbs as well.
So yeah, to back up here. So there's places in here like to have, kind of if you can see that enum there, but we have certain flag fields that are set that are provider specific, and when those are set, that means that only the provider would interpret. So this would provide a way, a verbs provider, even if it's a single NIC, right? You could expose your own capabilities through this framework. The idea is hopefully there's some commonality that we can have other vendors implement the same thing, but you could go directly to just a single verbs provider through this as well.
I see. Okay. Thanks.
Again, we're hoping that this also ties into like a collective offload, but something even more generic than collective offload. We would have a way through this interfaces to take advantage of those sort of offloads as well.
Hi, can you kind of scroll up towards the beginning about the different type of Smart NIC, different hardware? Yeah,
This
right
one?
there. So, kind of, I was gonna say you made a comment before, and I totally agree with that. Some of the FPGA silicon out right now, like even for like the Stratix 10, it's getting faster and faster for those transceivers. For example, for doing Ethernet transport layers, most of it is at the MAC layer, right? For some of the hard IP that's in there. Can you comment on any plans to help support making a Smart NIC with, say, an Intel FPGA, such in a form of other IP beyond the MAC layer?
We talk about it. Perhaps, I mean, I'm not sure. Is there anybody in Intel who can? I don't know. Maybe it's, but it's not. I mean, whatever is on the official product roadmap, we can talk about it. But okay, it's definitely feasible.
We can discuss.
Yeah.
All right. Thank you.
So just looking at the API you've sort of set there, I'm not sure how it fits very well with the kind of existing offloads we'd already see in kind of the verbs world, like for storage CRCs and whatnot. 'Cause those are all focused on MRs, not on QPs or endpoints. How do you see that working?
So whatever offloads that verbs has, we would need to make sure that this would end up mapping to, right? So this was looking at, I think maybe a different usage case than what you're referring to, right? You're not referring to FPGA stuff. You're referring to very hard-coded offloads, right? That you have.
What's the difference, right?
So,
I mean, if you're got an FPGA doing it or it's baked into an ASIC, it's a calculation you're doing on your data transfer. It's the same fundamental sort of problem you're looking at. And we have examples of this already. It's deployed in the kernel. We're using it on all the storage protocols. And it doesn't seem to fit what you've described here.
You mean having a memory region-based offload versus this is tying it to the endpoint,
Right.
as part of the transfer? Yeah. So that I would just have to, we have to think of how we want to expose something similar, or if there's a way to just map this to the same sort of mapping that you're talking about, right? Is it a memory region-based operation, or is it really something that needs to be a part of the transfer itself, specified as part of the transfer?
It's a good question, but
So-
the hardware implementation is all memory region based.
Well, that's the problem. So we don't want to tie it to a specific implementation, right? So this is, again, trying to be very generic because we want to be able to export any type of implementation and not necessarily bind us to exactly what one vendor did on one implementation. So that's where the challenge ends up being. I would say it needs to support existing implementations, but it can't be tied to an existing implementation. So I don't know what the final solution would end up being for all of it. I don't know if we've in the past we've pushed away from having memory region centric stuff where we can, but I know that there's like the portal specification is very memory region centric, and we do have in fact we have like mode bit type operations for memory regions, like where did I go back? Our bind operation, right? So I'm showing an endpoint bind, but the bind operation itself is generic. It can take any two objects. So you could easily reuse the same thing and say bind a network function to a memory region or a network function to a domain, right? So that through the API is flexible enough that we can support that. I only listed here the endpoint, but we could do bindings to memory regions if needed. What I don't know is whether or not that would have to be. We may have to expose mode bits as to how that binding occurs, which we have done with like RMA, for example. We have ways to say, are you binding memory region to an endpoint? I think counters might be. Counters to endpoints or counters, are we binding to memory regions? And we have bits where we set to indicate from the application which one they need to try to use. And we may need to have the same sort of way as how do these network functions apply? Do the network functions apply on the endpoint or at the memory region level? But I think the API is flexible enough that we could support both. It just may be more difficult on the application because now they have to figure out which way to use.
Well, yeah, that's always
Yeah.
been the problem with all this stuff is it's very difficult on the application to figure out which way to use it. But I mean, if you want performance in this area, you need to kind of match what the hardware is doing.
Right.
The hardware that's
I can say that
available today is MR based.
the biggest complaint we get with OFI is when there's a difference in the hardware and the applications have to adjust. So that's an extremely common complaint.
I've heard that complaint also. Yes.
So,
Okay.
but people don't want to give up the performance, but they don't want to deal with it, the pain of it either.
Yeah. Well, I mean, it would be nice if some of this was standardized in a more of a multi-vendor kind of way rather than just trying to, put the cart before the horse and standardize something in libfabric and then expect, I don't know, something nebulous to appear that somehow is interoperable, right? Like maybe this is a role for the revised OFA is to make more proper standards instead of, I don't know, this wishy-washy thing where everything's just a void star.
Right. Right. This is why this is very void star. This is the problem with the FPGA, right? Is I don't know what you're doing. You could implement any function, so you get int foo void star parameter. So.
But sure, but that just guarantees it's not actually usable and it's not actually general. And all you've done is give an API for one piece of software that's proprietary. You talk to a different proprietary piece of software through your little middleware. So I question that there's any value here in that tunnel, but maybe the connection to the other libfabric objects is really necessary. I don't really have a good sense of that.
I think it's a matter of it just needs to evolve, right? So people want to use it today, and the goal is that you can evolve, right? These well-known functions expand, right? So I didn't list it here because I don't have anything on the slide, enough room, but that you would have these actual well-known functions types that would be exposed. Like the atomics, right? The atomics are something easy that you can expose, but then MPI went further, right? They defined user-defined data structures, right? We don't have that here, but if there were certain structures that were common, we could put that sort of stuff in the atomics. If they became common enough. And it may be that the middleware becomes so reduced that, just TensorFlow or just MPI, that there's stuff that is common enough that we can put back into these lower levels.
Right, but mean, it's kitchen and egg. You can't put it in the common list until you have hardware that implements your common thing, and you can't have hardware until you specify. So, I mean, somebody's got to go first.
Yeah. Well, I don't know if we need the hardware. We need the applications to become common and drive that down. So if the applications are needing the feature and the capability, right, then we can put that in, even if the hardware doesn't support it. And then we just continue to do either the software emulation, which is what the application would have to do anyways, or drive it down.
Yeah, fair enough.
Hopefully that helps. We're keeping you from lunch now.
That's a heavy topic. Thank you.